Okay, so this is going to be section 7.7 and 7.8. We're going to start by talking about intermolecular forces today. And so intermolecular forces are the attractive forces between molecules. Inter meaning between. And so we have a few different forces we're going to look at today: London dispersion, dipole-dipole, and hydrogen bonding. So the strength of the intermolecular forces determines if it has a high or low melting or boiling point, if it's a solid, liquid, or gas at given temperature. I mean, basically, those are the same things. What I want you to think about as far as this is the stronger the intermolecular force, or the intermolecular force, sometimes we call this IMF. So the IMF is like a glue holding the molecules together, or the particles together, because it can be atoms as well. I don't want to say atoms here because I don't want you to get confused with bonds. And so just an FYI, bonds are ionic and covalent interactions between atoms, and these are intramolecular forces. So between or in or within. So bonds are intramolecular forces within the molecule. Intermolecular is like between one molecule of water and another molecule of water, not the covalent bond between H and O, if that makes sense. So the IMF is like glue holding the molecules together. So the stronger the glue equals harder to pull apart. And so harder to pull apart equals higher melting and boiling points, because we got to put more energy in to pull them apart. And to melt, to turn into a liquid, or to boil, turn into a gas, we have to separate the particles. So remember when we talked about the differences in solids, liquids, and gases, and I said pay attention to the distance between the particles. For solid to liquid, you have to increase distance. For liquid to gas, you have to increase distance. And so if it's harder to increase the distance, it's harder to pull them apart, you have a higher melting point or a higher boiling point. So the first force we're going to talk about is London dispersion forces. Those are weak interactions, and they're due to momentary changes in electron density. So electron density, like where all the electrons are, if there's an area that has a lot of electrons or an area that has a smaller amount of electrons. This creates a temporary dipole, so it makes a temporary polarity. All covalent compounds and all atoms exhibit London dispersion forces. Basically, everything does this. If it has electrons, it can have this. And it is based on momentary polarity. So I think I have a picture here for you. So let's just say that you have a lot of electrons hanging out over here for some reason. And the electrons are constantly randomly moving around. And then that creates a negative over here and a positive over here just for a minute, because my electrons just happen to be more over here on the left side. This positivity here will attract all the electrons over on this molecule to kind of join up on this side. And so the electrons are kind of randomly, constantly moving around the molecule. So they're floating around in these orbitals, like around the molecule. And so they will kind of come over here because they're attracted to this side. We use this little partial here to indicate partial charge. We've looked at this before with polar molecules, I believe. But the intermolecular force is the attraction between those molecules. And this is momentary. So think about this as like flashing on and off, like a fireflies flashing on and off, because the electrons are constantly moving. So the next moment looks different. Maybe the electrons are more evenly distributed and there's no charge. In class, I'll draw you another diagram to kind of try to help with this understanding. Dipole-dipole interactions are the attractive forces between two actual polar molecules. So dipole-dipole means polar-polar. So polar molecule and a polar molecule. So who can have dipole-dipole interactions? Polar molecules. If it's not polar, it cannot have dipole-dipole interactions. So polar molecules have London dispersion forces because they have electrons, but they also have these dipole-dipole interactions, and these are permanent dipoles. So this is always one side is positive and one side is negative, but it's essentially the attraction between the positive and negative side. So it's the same idea, except this one is kind of momentary. It's blinking on and off. It's not on all the time. This one is permanent because the molecule is always polar. This side here is always more negative because that's an oxygen, right? This carbon will always be a little positive because it's got electronegativity pulling this way. And then hydrogen bonding is just a special type of dipole-dipole. This is the, it's just because the hydrogen is very small and oxygen's very electronegative. So it's just like, this one is super, super, this is like really positive. And this one is like really negative. So it's the same idea as a dipole because we have two polar, but because the oxygen's electronegativity is so high, it really makes a bigger difference. And so we look at hydrogen that is bonded to an O, an N, or an F. So it has to be on one molecule, the O, N, or F, and the other molecule has to have a hydrogen bonded to O, N, or F. And so the hydrogen bond is not the bond between the hydrogen and the oxygen. I know it's called bonding, but it's not really a bond. It's really an intermolecular force. And so you must have HO, HN, or HF, and a lone pair of electrons on N, O, or F. And if you're going to do hydrogen bonding. Hydrogen bonding is the strongest one because it's just like extra strength dipole-dipole. Hydrogen bonding is really special. This is what holds together our DNA, for example. And so how do we know that, the base pairs do what they do? Is because they match up hydrogen bonding in different ways. And so that's how the DNA knows where to go together with the double helix. So here's a little summary of the three intermolecular forces we're going to look at, how their strength, who has them, and some examples of things that do have them. So how does this affect boiling point and melting point? So remember, we talked a little bit about this, but I just want to make sure we understand. Boiling point is when liquid goes into gas. Melting point is the temperature at which solid goes into liquid. The stronger the glue, the higher the boiling, the melting point. So hydrogen bonding would be stronger. Sometimes you can have London dispersion have a higher boiling point because it's just very big. We'll talk a little bit about that in class, but basically if you can look at if you have three different forces, the one that has hydrogen bonding is going to be the highest melting or boiling point. If you have all London dispersion forces, let's see. Yeah, I think we'll talk about this. So boiling point and melting point, let's look at these two, methane versus water. This one is London forces only, and this one is hydrogen bonding. It has all three of them, but hydrogen bonding is the strongest. Notice the boiling point is much higher and the melting point is much higher. These are negative numbers. And so this one is very low, this one is very high. So stronger forces, higher boiling point, melting point. Now, what if both of these have London dispersion only? So London dispersion only, LDF, London dispersion force only. So what if they all have London dispersion? How can we rank them as far as boiling point? Well, the more electrons you have, or the more mass you have, the larger the molecule, stronger London dispersions. Because the more electrons you have, the more likely your electrons are gonna be off center a little bit. So the more opportunities you have to have that connection, to have that glue. And so we see changes. Now notice it's not as drastic of a change as the hydrogen bond, but it is a change. For liquid stuff, we talk about changing into and out of liquids. Evaporation is liquid into gas, and it is endothermic. So we are absorbing heat from the surroundings. So in order to evaporate something, the water has to have heat go in. So you have to put energy in to evaporate water to turn it from liquid to gas. But that's what we would think about as boiling water on the stove, right? We're turning liquid into gas. Condensation is the opposite. This is like gas, like steam turning into liquid, condensing on your mirror. This is exothermic. It gives off heat. So if you can think about particles moving apart, you have to put in energy to separate them because they're attracted to each other. You have to break the intermolecular forces, the glue. So that's endothermic because we have to put in energy to break them apart. If the particles are coming closer together and particles, and you also can think about particles as speeding up with a lot of these changes, but particles slowing down, coming together. We get out energy because now they're more stable when they're glued together with IMF glue in place. So this is exothermics, kind of like making a bond and breaking a bond, except we're not talking about bonds, we're talking about interactions between molecules, but it's the same kind of idea. All right, I think this is the last little bit here. Vapor pressure. So vapor pressure is the pressure exerted by gas molecules in equilibrium with liquid phase. We talked about equilibrium a little bit. So really what we have at the top of every liquid, you have this equilibrium between the liquid and the gas version. You've experienced this. If you've ever had a bottle of water, you leave it in the car and it goes, even though it's not, when you open it, it makes a sound, right? You're releasing that pressure, even though it's not carbonated. That's because the vapor, the water vapor, there's always a little bit of gas turning into a liquid turning into gas even before you get to that boiling point. There's a little bit of that happening because some particles just have enough energy to pop out. So imagine it's like dolphins on the ocean. So the particles are jumping out into gas phase and then going back into liquid phase. So it's an equilibrium. They go back and forth. The more energy your particles have, the more of them can be up in gas phases. So the vapor pressure increases with increasing temperature. So that's why you have your hot water bottle. It's gonna, when you open it, will say, even if it doesn't have carbon dioxide in it. So the boiling point of a liquid is the temperature at which the vapor pressure is equal to the atmospheric pressure. So this is our atmospheric pressure. So when the pressure of the vapor equals the pressure of the atmosphere, then everything gets to turn into gas at that point because they're pushing each other. And again, we'll go over this in class a little bit more and I can help you with the concept of that. The stronger the intermolecular forces, the lower the vapor pressure because the harder it is to separate into gas. So water has strong intermolecular forces. It has hydrogen bonding. So its vapor pressure is low. We don't talk about water as being volatile, right? As being something that like turns into vapor. Like gasoline, for example, is volatile, or alcohol, acetone, these things where if you spill a liquid, you're going to smell it. It's because it turns into a gas really easily. Weaker intermolecular forces turn into a gas really easily. So they'll have higher pressure of gas, even if they're in liquid form. Oh, and then these last two are related to intermolecular forces as well. So viscosity is the resistance to flow. So viscous feels thick. I want you to think honey. Honey is very viscous. It doesn't flow, it's thick. And so it has a really strong intermolecular force because honey is a sugar and a sugar has hydrogen bonding. It's a really big molecule. It's got a lot. So it's a large molecule. Water has hydrogen bonding, but it's a smaller molecule, so it's not viscous as much because it is, even though it has really strong glue, it's a small amount of it, versus like honey is a strong glue and it's a lot of it. And surface tension is a measure of the resistance to spread out, a resistance of a liquid to spread out, so they hold together. You can imagine, so if the glue is stronger, then it holds together on the surface. And so you get little bugs that can, walk on the water, or these little water striders or things like that. And so we can think about just the intermolecular forces as glue, and these things make a lot more sense. So if they're stuck together because they're sticking together, they're not going to flow freely. They're not going to come out of a container as easily. If it's not stuck together, it's easy to get it out. And then if it's stuck together more, it can hold something on the surface. It can support something on the surface. If it doesn't stick together well, you try to get into it, you'll just fall through. So the stronger the intermolecular forces, the higher the surface tension, the higher the viscosity. Water has a very high surface tension because of its hydrogen bonding. All right, that's the last part for this video. We'll see you later.